Okay, so let's dive into one of the most influential books in machine learning. But we're not here to grind through a bunch of formulas. Nope. We're here to learn a way of thinking, to really get at the core principles that separate someone who's just starting out from a real expert.
Right from the preface, way back in 2006, the author Christopher Bishop was pointing to this huge shift happening in the field. He was basically saying the future isn't about demanding perfect certainty from our machines. It's about intelligently and mathematically embracing uncertainty.
And that's why people often call this book a Bible of the field. It's not just a grab bag of algorithms. It's more like a guide to the fundamental principles. How to teach machines to learn from data, how to reason, and how to make predictions. So the crucial point here, really, is that to truly get good at machine learning, you have to go deeper than just the code. It's all about grasping these core ideas, and that's exactly what we're going to unpack. All right, now let's get into what is arguably the single most important challenge in all of machine learning. It's called generalization. And this is the absolute heart of the problem.
So, what is generalization? Well, it's a model's ability to make good predictions on stuff it's never seen before. I mean, think about it. A model that just memorizes the training data is totally useless, right? The real test, the only test that matters, is how well it predicts the future.
Okay, so look at this. This slide shows what happens when our model is just too simple. This straight line completely misses that nice wavy pattern in the data points. It's just not flexible enough. This failure has a name. It's called underfitting.
But now, check this out. We give the model a little more complexity and, bam, it finds the sweet spot. This curve is flexible enough to see that underlying sine wave pattern, but it doesn't get distracted by all the little random jitters. This is what a good fit looks like. This is the goal.
But here's where the danger lies. If we make the model too complex, it just becomes obsessed with the training data. I mean, look at this thing. It zigzags around to hit every single blue dot perfectly. But in doing that, it's learned the random noise, not the real signal. This is called overfitting, and it is a disaster when you show it new data.
So, how do we find that perfect Goldilocks zone? Not too simple, not too complex. Well, the book argues for this really powerful shift in perspective, a truly expert way of thinking. You stop demanding a single right answer, and you start to embrace uncertainty.
See, the standard approach, a lot of the time, is to try and find that one single best-fitting curve. But the Bayesian approach, it does something completely different. Instead of just one answer, it considers all the possible curves and gives each one a probability based on how well it fits. It's a whole spectrum of possibilities, not just one point.
And this just brilliantly shows the power of thinking that way. The model gives us a prediction, that's the red curve, but it also tells us how confident it is. See how that shaded red area, the uncertainty, is really narrow where we have data points, and then it gets super wide where we don't? That is a model that knows what it doesn't know. That's huge. Okay, so even with the right philosophy, an expert knows you're going to run into some really weird practical hurdles. And one of the strangest and most important is this thing called the curse of dimensionality. It sounds like a total paradox, right? You'd think that giving a model more information, more features, more dimensions, that's got to be a good thing. But what happens is in these really high-dimensional spaces, our normal human intuition just completely breaks down, and learning gets incredibly hard. So think about it like this. In a simple two-dimensional space, your data points are pretty close to each other. It's easy to find neighbors and learn local patterns. But every single time you add a new dimension, the volume of that space just grows exponentially. It gets empty fast. This graph looks a little crazy, but what it's showing us is mind-bending. As the number of dimensions, that's d, goes up, almost all the volume of a sphere gets pushed out into a super thin shell right at its surface. And the consequence of that? Every single data point becomes its own isolated island, super far away from every other point. It becomes almost impossible to learn from your neighbors.
So, how do experts deal with these massive challenges, like generalization and dimensionality? Well, they don't just memorize a list of disconnected algorithms. They use these core principles, managing complexity, quantifying uncertainty, as a kind of unified toolkit that they can apply everywhere. So let's see how these big ideas aren't just some abstract philosophy. They are the actual bedrock for the advanced, practical models that you hear about all the time. Take kernel methods, for instance. They're the engine behind powerful models like support vector machines. They are built on these exact principles, using these clever mathematical tricks to find complex patterns that would be totally invisible to a simpler model.
Or how about in the world of neural networks? Techniques like this one, tangent propagation, they explicitly teach the model how to generalize. It's basically helping the network learn to ignore stuff that doesn't matter, like if a handwritten number is slightly rotated. It helps it focus on what really makes it a 7 or a 4.
And to fight that curse of dimensionality we just talked about, experts use tools like probabilistic PCA. It is a really smart way to cut through the complexity, to find the most important underlying patterns in the data, even when that data is messy or has pieces missing. And by carefully managing that model complexity, advanced generative models can uncover these incredibly intricate nonlinear structures. Just look at the difference here. On the left, a simple linear model is just struggling. It's a mess. But on the right, a more complex model reveals the true patterns with amazing clarity.
So when you really boil it all down, thinking like an expert isn't about memorizing hundreds of algorithms. It's about deeply understanding these foundational principles. Master generalization, embrace uncertainty, respect dimensionality, and you'll start to see how this entire huge field of machine learning really connects into one coherent picture.
And that kind of leaves us with a final thought. As our AI models get more and more powerful and their outputs start to feel almost magical, these expert principles serve as a pretty critical reminder. Maybe, just maybe, the most important knowledge of all is having a clear understanding of what you don't know.